Welcome to The Explainer. You know, our whole world basically runs on a steady stream of electricity. But what happens when nature decides to throw one of its most powerful punches right at it? Well, today we're going to pull back the curtain on the unsung hero of our electrical grid, the lightning arrestor.
So to really get why this device is so important, you first have to appreciate just how big the threat is. We're talking about a single bolt of lightning, a crazy surge of energy that can top 1 billion volts. It's totally unpredictable, incredibly destructive, and it's always looking for the quickest way to the ground. And guess what makes a fantastic target? Our power lines.
So that's the big question, isn't it? How on earth do you design an infrastructure to handle that kind of energy? How do you stop those transformers and substations, the stuff that costs millions of dollars and keeps our lights on, from getting completely vaporized in a millisecond?
Well, the answer is this really clever device called a lightning arrestor. And its mission, when you break it down, is simple, but at the same time, it's incredibly difficult. It has to catch that massive surge of power and give it a safe detour, all in the blink of an eye.
Honestly, the best way to picture it is like a super fast pressure relief valve, but for electricity. When the voltage is normal, it just sits there, does absolutely nothing. But the second it senses a massive spike, bam! It opens up to relieve the pressure, protecting everything down the line.
The whole job really comes down to 3 crucial steps. First, you've got standby mode. This is where it lives 99.9% of the time, acting as an insulator totally invisible to the grid. But when a surge hits, that's action. It flips a switch and becomes a conductor instantly. It basically creates this low-resistance superhighway for all that dangerous energy to travel safely straight to the ground. And then, just as fast, it has to reset right back to being an insulator again.
But look, to pull off this high-speed, high-stakes job over and over again, an arrestor needs a very specific set of skills. This isn't just a simple switch we're talking about. It has to be a seriously refined and reliable piece of tech.
Okay, first up, and this one is absolutely key, is a concept called residual voltage. Now, this isn't the voltage from the lightning itself. This is the little bit of leftover voltage that actually gets past the arrestor and reaches the equipment while the arrestor is busy diverting that main surge.
And this is exactly why it matters so much. Even with the arrestor doing its job, the equipment it's protecting still feels this little zap. So the lower an arrestor can keep that residual voltage, the less stress there is on that expensive transformer sitting next to it. It is literally the difference between a close call and a catastrophic failure.
All right, next up is a tricky little problem the arrestor can actually cause for itself. It's called follow current. See, after the lightning surge is gone, the grid's normal power is still there. And since the arrestor just opened up a nice path to the ground, that normal system power wants to do exactly what the lightning did and follow it right down. This is so critical. The arrestor has to be able to slam the door shut on that follow current instantly. Because if it doesn't, the grid's own safety systems will see it as a short circuit, a fault, and they'll trip a breaker, causing a power outage. So, a great arrestor doesn't just save the equipment, it does it without causing a blackout.
So, if we put it all together, you get this kind of hero's checklist. A top-tier arrestor has to react to surges in a flash, but completely ignore normal voltage. It keeps that residual voltage super low. It's a master at cutting off follow current. And it's got to be tough enough to take multiple hits over many, many years without breaking down.
All right, so that's all the theory, but how does this stuff actually get used out in the real world? Because where you put an arrestor and which one you pick, well, those are some seriously important decisions.
Arrestors are rated by how much current they can handle, which is measured in kiloamperes, or Ka. And it makes total sense, right? The rating gets bigger depending on how critical the location is. So a 2.5 Ka arrestor is perfect for protecting the local power lines on your street. But for the massive power plants and major substations, yeah, you're going to need the big guns, the 10 Ka units.
Now, besides that rating, when it comes to actually installing one of these, there's a specific number that engineers are almost obsessed with. And it's probably a lot smaller than you think.
20 meters, that's it. For a typical distribution system, that is the absolute maximum effective distance you can put between an arrestor and the transformer it's supposed to be protecting. Any further away and the voltage can actually build back up in the wire between the two. So placement is everything. To be a good guardian, you have to be standing right next to the thing you're guarding.
Okay, so let's just zoom out for a second and look at the big picture. Why do we go through all this trouble to engineer such a specific, sophisticated little device? Well, the difference between a grid with them and a grid without them is just night and day.
With arresters, you've got a resilient power system. It's got a built-in defense mechanism that shields equipment and keeps the lights on. But without them, the grid is just vulnerable. A single thunderstorm could set off a chain reaction, destroying incredibly expensive hardware and causing blackouts that could last for days, maybe even weeks.
When you really think about it, the lightning arrestor is the perfect definition of a silent guardian. It just stands there, day in and day out, waiting for a threat that lasts for only a few millionths of a second. We never even notice when it does its job successfully, but it is absolutely fundamental to the reliable world that we all depend on.
And that kind of makes you wonder, doesn't it? What other invisible, unsung heroes are out there, quietly doing their jobs, making sure our incredibly complex world just keeps on ticking? Thanks for joining this explainer.